today, I'm going to write some problems up here and let you work together, work through them, just get used to, get these derivations sort of in your muscle memory and stuff. Okay. Does anyone have any homework questions first?
Number 4.
Okay. Well, forget my plans. Let's do number 4. Okay. Before that, our final is Friday, 12:20 at 8 a.m. So sorry about that. I didn't make that decision. I don't like it either. Hopefully it'll be warmer than this morning at 8 a.m. Oh, that's good. I think last winter I just convinced myself we're done with winters in Minnesota. I never have to worry about that again. So that I'm taking this hard this year. I know. Well, I think that's what I think my subconscious told me that's where we are with global warming. No more Minnesota winters.
Not so.
No. Apparently that's. What? Oh.
Swings are more dramatic.
Yeah. Halloween snowfall.
Yeah.
I thought I followed the way it just was kind of flat.
Okay.
And came up with 2 to the 30.
2 to the 13?
Yeah.
That's a lot. Okay, so we have a 10,000 Newton force on one side, and so first we're going to say that it doesn't wrap a full time around. It just does that quarter turn. And we're going to start with the derivation, and then we're just going to we'll get the formula, and then we'll use the formula. I suppose we can just plug things in as we go. Okay, 10,000 newtons of force there. So here is our little infinitesimal piece of the cable. What?
Yeah, right.
Yeah, exactly. So over here is, so with this picture, you can see that on the right side, that's going to be the high force side, and it's going to be the low force side over there on the left. So I'm going to make I'm going to call this T, and I'm going to make this T plus dt. Maybe I'll make it deltas to start. For the skeptics, I'll just make them deltas. Everyone can buy it so far. It's the frickin' limits that get you. Yeah. Okay, we're going to, so what other forces are acting? We have a normal force here. This is a small little bit of normal force. And we have a friction force here. So this is our coefficient. We're given a coefficient, that's 0.4. So this is going to be 0.4 delta N. Everyone with me on that so far? Mm-hmm. And now, so for dimensions, this is going to be our change in theta. And so when we go to Newton's second law, we have negative 0.4 delta N, and then delta N for Y. And our T is negative T times the cosine of delta theta over 2, because you can think of each one of these two sides of this little piece as angling down delta theta over 2 to give you the full angle of delta theta. You also could do this with the t side vertical, you know. You'd get the same things at the end, and then you'd just have your delta theta over on the other side. If that doesn't make sense, ignore it.
So that delta theta over 2 is that little angle from the top.
Yeah, this is delta theta over 2, and this is delta theta over 2. And the sign there is negative t, the vertical component, negative t sine of delta theta over 2. And then on the other side, we have t times the cosine of, no, we don't. We have t, plus delta theta times the cosine of delta theta over 2. And then for y, we have t plus delta theta. This is negative again, times the sine of delta theta over 2. And we're in static equilibrium, so this is equal to zeros. And so now we get our two equations, negative 0.4 delta n minus t cosine delta theta over 2 plus t, I'm going to distribute this out, cosine delta theta over 2 plus delta theta cosine delta theta over 2. And then for the y component, and my ear still frostbite's easy because of that. 32 years later.
Those old,
Stupid cross-country meet. I should have even been running. I was injured.
Is it like, can you tell when a storm is coming?
I can tell from the inner part of my ear if someone tells me a storm is coming. Okay, delta n minus t sine.
Before they invented safety.
And then minus t sine delta theta over 2 minus delta theta times the sine of delta theta over 2. Okay, so now we're going to take the limit. Now here is where you might have concerns, but we're going to do it anyways. So we're going to take the limit as delta theta goes to 0. And what we get is negative 0.4 dn minus, so now if you take the limit as delta theta over 2 goes to 0, this just becomes delta t, okay? The limit of the cosine of x as x goes to 0 is 1, okay? This one, same thing, so this is plus t. And then this one is d theta. And now our y equation says dn. And now the limit as x goes to 0 of sine of x is different. As you take the limit as x goes to 0, sine of x just goes to x when you're in radians. And so this becomes negative t d theta over 2 minus t d theta over 2, and then minus d theta times d theta over 2. Did I do that right? I don't remember there being a double theta there, I guess. Oh, because there's not. Okay, so I caught something I messed up here. This is supposed to be obviously t plus delta t. Okay, and so that means that this should be delta t. This should be delta t. I think that's the only mistake I made on those. And that means that this should be dt. And this should be dt. And now we'll cancel some stuff. Those cancel. These two group. And we can write our final form of this equation as negative 0.4 dn plus dt is equal to 0. And this thing here, so we're talking about infinitesimally small things. And so if you square infinitesimally small things, they have no relevance to your calculation. And so this goes to 0. And so the second equation says dn minus t d theta is equal to 0. Okay, so now we're going to eliminate the dn's from this. This is kind of like our final system of differential equations. We'll solve that by saying dn is equal to t d theta. And we'll plug that into the x equation. And that says that negative 0.4 t d theta, I'll move this over to the other side, so 0.4 t d theta is equal to dt. And now we can integrate both sides. If we move the t over, we're going to separate variables. So we get 0.4 d theta is equal to dt over t. And we are going to integrate this from, so like from theta 1 to theta 2. And this is from tension 1 to tension 2. So we are going, I guess we're going to call this our theta 1 and our T1, and we're going to call this theta 2 and our T2. So this is the integral from an angle of 0 to an angle of pi over 2 radians. I can pull the 0.4 out. And that's equal to, so our T1 is 10,000, our T2 is T. And we get 0.4 times pi over 2 minus 0 is equal to the natural log of T over 10,000. So you can write this as 0.2 pi is equal to natural log of the quantity T over 10,000. And now raise both sides as a power of E. So you have T over 10,000 is equal to E to the power of 0.2 pi. And so T, I went the wrong damn direction. How did I do that?
Direction.
Well, so this, I got a bigger value for T. I went, so 10,000 E to the 0.2 pi. Okay, so I,
That's 18,000.
yeah, well, I mean, the whole point of this is that you get a smaller force over here. So I just went opposite directions in my integration somehow. Do I see how? So this, so I went, so this thing, okay, so, well, my delta theta is going this way. If you look at all these deltas need to go in the same direction. So my delta theta is going this way. So I need to be going from theta 1 to theta 2 here. To be honest, an easier way to avoid this mistake, so that means that if I'm integrating from left to right, this has to be from T2 to T1, the way I have it drawn. And so this is 10,000 over T, or in other words, this is negative to get this. And so T over 10,000 is equal to E to the negative 0.2 pi. And so T is equal to 10,000 E to the negative 0.2 pi. So what do you get here?
5334.9.
Okay, so how would, it would be better to avoid, it would be better to avoid this problem here. So to do that,
I mean, is it like a good idea to like be like really distinct about your direction? Like,
yeah, exactly. So I'm just trying to think how to, so let's say, I would say just
oh, because
always,
so is it because your delta t was going to the right there in your picture?
yeah,
Plus delta t.
yes,
So you
all
can,
of your deltas need to agree with each other, you know.
okay.
But let's think of a way to just avoid that situation altogether. So
even if we had the plus delta t to the smaller side, that could have still worked out to be a smaller value than that 10,000.
in this, so it's because I have the t plus delta t coming over to this side that corresponds to a bigger delta theta, you know. And so then when I did my integration bounds on the theta, I went the opposite direction. So let's come up with just a system where you can always do it the same way and you won't ever have to worry about that. So let's say that we're always going to go from, so our theta 1 is always going to be on the left. And our theta 2 is always going to be on the right. Okay. Then I could have gone, I mean, and that just corresponds with the way that I'm drawing this picture.
So that in that case, then you can always kind of do it the way that makes sense, like in terms of like angles.
Right.
Starting at 0 on the right.
Yeah. Right.
That's what you're saying.
Right. Right. And if in this case you have the bigger force over on the right, I would say if you have a case where just always think of your instant 1 being on the left and your instant 2 being on the right. No matter which one is bigger or smaller, just plug those in, you know.
Mm-hmm.
But so now we have this expression that says, let's just go from here to sort of like a general formula. So you derive that general formula and then you can just plug stuff in. So this is going to be, so let's think of this as 0.4 times the integral of from theta 1 to theta 2 d theta is equal to the integral from t1 to t2 of dt over t. And then we'll integrate that and get 0.4 delta theta is equal to natural log of delta t. That's not right. Natural log of t on the right over t on the left. And now in each of these two cases, you can just plug this in. So let me clean this up a little bit. So this is 0.4 times theta on the right minus theta on the left. And then you can just think of this as do it in the positive direction and do this in the way where t on the right is greater than t on the left. This isn't making a lot of sense, I know. Let's go through this derivation again for the second part, and I'll do it in a way that's easier to remember. But so now that you have this, you just have a formula you can plug in, you know, where you have, you can think of it as like 0.4 delta theta is equal to the natural log of t big over t small. And you always know you can sanity check your answer. I mean, you know you're given in the problem which one of these two is bigger than the other one. And you know that you want the bigger one over the smaller one if you have a positive on your angle side. Are you with me on that? So in a way, you can just skip over the real like nitty gritty thinking about it and just get your signs to make sense. So let's do it again now. So this was the answer for a quarter turnaround. Let's do it now for the full turnaround, and I'm going to do the whole derivation in kind of a simpler way, an easier way to remember. Okay. David's like, he's like looking at it like, I know it's the infinitesimals that made this such a pain. Okay, so let's do it again, and let's just derive the formula. I have to level with you, okay? This is the first time I've taught this class and made you remember this derivation. I've always just told you could use the formula, but
I actually sort of appreciate this.
As human brains,
I breezed by this in calculus.
Yeah, as human brains evolve, I need to keep us expecting more out of the students. Okay, so we got over here we have t. And we have delta n. And over here we have t plus delta t. And since the force is pulling to the right, the friction force has to be this way. So this is our, this would be our mu times delta n. In our case, mu is 0.4. So we have this. And for angles, we have d theta. Okay, so Newton's second law says negative t cosine of delta theta over 2, negative t sine of delta theta over 2, plus negative 0.4 delta n, plus t plus delta t quantity times cosine of delta theta over 2. And then for the vertical component, negative quantity t plus delta t times sine of delta theta over 2. One, 2, 3, 4, okay. And this is all equal to zeros. And so now I'll break it up into an x and y equation. So we have negative t cosine of delta theta over 2 minus 0.4 delta n plus t cosine delta theta over 2 plus delta t cosine delta theta over 2 is equal to 0. And we can cancel this stuff here. And then our y equation says negative t sine delta theta over 2 plus delta n minus t sine delta theta over 2 minus delta t sine delta theta over 2. And now we'll take the limit as delta theta goes to 0. So we have negative 0.4 dn plus dt times the cosine of basically 0 is 1. And then for the y equation, we have negative t times the sine of d theta over 2 is just d theta over 2. We have 2 of those, so I'm just going to combine them here. Plus delta n, and the nonlinear term goes away because it's extra small. And so there's our system of differentials. Anybody have any questions about getting there? I did skip that step of, I could have drawn it out one more time with the infinitesimal stuff, and then we could have used the limits to cancel stuff, but I sort of did that in my head as we went.
How do we get that d theta for the 2 negative t sine?
Okay, because sine of d theta over 2, as this d theta goes to 0, this goes to just d theta over 2. And so we end up with these 2 terms that are negative t d theta over 2, and then we can just add them. Okay, so now we know that, and this should be a d. And now from the y equation, we can see that dn is equal to is equal to positive t d theta. And so plug that into the x equation, and you get 0.4 t d theta is equal to dt. Get all the t's on one side, and you have 0.4 delta theta is equal to dt over t. And now you can integrate both sides. And you get 0.4 times, if you think of one of these as 0, you can just write this as 0.4 theta, is equal to the natural log of t2 over t1. And we'll just think of this as positive. No matter which way you want to think about it, just think of this as positive. And then correspondingly think of this as the bigger tension over the smaller tension. And then you don't have to think about directions and stuff. So now for the second one, okay, so we derive, do the exponential thing, and you get that T2 is equal to T1 E to the 0.4 theta. Okay, so we got this formula. And the T2 is the big one, and the T1 is the little one. So now we're going to do it for the second case, where instead of this theta being pi over 2, it's 2 pi plus another pi over 2. It's going it's wrapping around one full time and then another quarter. So what is that? 5 pi over 2, right? Okay, so we got our T2 was, what was that, 10,000, the big one? So 10,000 is equal to the T we're trying to find, because it's the smaller one, times E to the power of 0.4 times 5 pi over 2. So you can write this as T is equal to 10,000 E to the negative power of, I guess that's 0.2 times 5. So this just ends up being pi, I think, right? Wyatt, you. 0.2 times 5 is 1 times pi, so that looks right. And so T is just equal to 432.1 newtons. So this 10,000 Newton force, you're supporting it with virtually nothing fractionally, by wrapping it one full time around. Cool. Right? I defy anybody to tell me that's not cool. Even David.
Turns out the mistake was using degrees instead of radians.
Oh, yep, that'll do it. Yep, for sure.
That's a much larger exponent.
Yeah, exactly. Yeah, that'll do it.
This definitely confirms my tree house building techniques.
Oh, yeah.
As a kid, it's like
you wrapped it.
You wrap it around that tree, that rope is not going anywhere.
Yeah, that's true. You probably get a pretty good coefficient of friction between bark and rope too.
Mm-hmm.
Yeah.
Yeah, when I was a kid, my mom got a helicopter cargo net, from Axeman, and we roped it up into the tree and used it like a playground cargo net.
Yeah. I mean, so that one time around gave us more than a factor of 10 difference in the force you needed to support it.
Cool.
Okay, so I would say all this stuff, don't mess with thinking about the bounds of those integrations based on the direction that you're working. You'll get yourself all confused.
But if I was, the trick would have been to integrate from the bigger angle. All of your deltas in your original equation have to correspond to the same direction, right? So don't think about the bounds of integration in terms of directions. Just think of your delta theta as positive, and your T2 over T1 as greater
than 1. Okay. Okay, well, I guess I'm just about done with telling you about statics.
So sad.
Yeah, we've had some laughs. We've cried some tears. No,